Ma'am, now you are host, madam. No audio, ma'am. Audio is muted for you.
Make you co-host, sir?
Yes, ma'am. That's all, ma'am. Everything is over. Live streaming also on. So you can take, ma'am.
Anybody else make co-host? Sir?
Make me as co-host, ma'am.
I made na?
Yes, I will change the name. Wait.
Prasanti also I make. Deepa is not seen.
Hello, good morning, ma'am.
Good morning, sir. Welcome.
Thank you very much.
Just I was thinking of you. You joined just to call you.
Oh, okay. So probably we will start at 10, right?
Yes, sir. Exact 10 will start. Just we are waiting for the participant because we have given the time 10.
Okay. No problem. I can.
But you welcome, sir. Just 5-10 minutes. We'll wait and we'll start, sir.
Okay, sure.
Good talk. स्टार्ट करिए.
Hello, Aman.
Yes, sir. Welcome. Neeraj, sir.
Yeah, I'm here.
Welcome, sir. Happy to see you.
Yes, ma'am. I think I can start now, right?
Yes, sir. Already it's going to.
Good morning to all. A very warm welcome to all the participants to this international conference on wireless sensor networks, ubiquitous computing, and applications 2021. My name is Dr. Surabhi Gupta, and I'm the co-convener for this conference. Today, we have scheduled a pre-conference expert talk for all of you. Now, I would like to request Dr. Padmalya Naik ma'am, who is the organizer of this conference, to formally welcome the first expert for the day, that is Dr. Neeraj Kumar. Over to you, Padmalya ma'am.
Thank you, Dr. Surabhi. Just I'll 4-5 lines only I'll speak, then you will introduce the speaker.
Yes, ma'am.
So wish you all very good morning, respected dignitaries, GRIT management, Principal GRIT Dr. J. Probin, invited speakers Dr. Neeraj Kumar, invited guests, HODs and deans, faculty and students of Punjab Technical University, all the participants of ICWSNUCA 2021 across the globe, and my dear colleagues and students. Hearty welcome to all of you on behalf of ICWSNUCA 2021 organizing team. The conference inaugural will be held tomorrow at 9:45 a.m. Today, we have arranged only pre-conference talk for 2 sessions to bring the awareness among the researchers. So one session will be handled by Dr. Neeraj Kumar, Thapar Institute of Engineering and Technology, and other session will be handled by Mr. Raghunandan Reddy, Senior Research Data Science Analyst, H. Lee Moffitt Cancer Institute, Florida, USA. Dr. Surabhi Gupta, one of our co-convener of ICWSNUCA 2021, will introduce and will start the session immediately. Let us enjoy the pre-conference talk and learn from the experts. Have a great day. Namaskar. I request Dr. Surabhi to introduce our speaker, then we'll start the session.
So let me formally welcome a professor in the Department of Computer Science and Engineering, Thapar Institute of Engineering and Technology, Patiala, since 2000. In CSC from SMVD University, Katra, Jammu and Kashmir, India. He was a postdoctoral research fellow in Coventry University, UK. Dr. Neeraj is an internationally renowned researcher in the area of VNet, CPS, smart grid, IoT, mobile cloud computing, big data, and cryptography. He has published more than 200 technical research papers in leading journals and conferences from IEEE, Elsevier, Springer, John Wiley, and Taylor and Francis. He has an H index of 68 with 15,964 citations to his credit. He's a member of the Cyber Physical Systems and Security Research Group. He has research fundings from DST, CSIR, UGC, and TCS. He has total research funding from these agencies of more than 2 crores under different schemes from the GUI. Recently, he has also got international research projects under DSP Research Initiative. He is editorial board member of International Journal of Communication Systems, Wiley, Security and Communication, John Wiley, and Journal of Networks and Computer Applications, Elsevier. He has visited many countries, mainly for the academic purposes. He's a visiting research fellow at Coventry University, UK. He has many research collaborations with premier institutions in India and different universities across the globe. He has been engaged in different academic activities inside and outside the institute. He has supervised 5 PhD students and 5 are currently pursuing their thesis. He has also supervised more than 20 ME MPhil theses. So a warm welcome to you, sir. And sir will be taking up the topic CNN for IoT applications today. So now over to you, Neeraj, sir.
Yeah, I'm here.
Yes.
Okay. So, very good morning to all of you. And first of all, I would like to thank the organizers of this conference, International Conference on Wireless Sensor Networks. So, to give me this opportunity to share my ideas on the latest technology, that is machine learning and data analytics techniques. So it's a good initiative, and I would also like to thank Neeraj sir to invite me for this pre-conference talk. So it has been a wonderful experience with Neeraj sir over the last many years, and we have been in touch with him for the many years. So today's point of discussion is basically the how we can use CNN for IoT applications, and how this CNN, that is convolution neural networks, had been used in wide range of applications, and it is everywhere nowadays. You can see that more of us, many of us are talking about machine learning, deep learning, data analytics. Then we have I mean to say here, a number of technologies that are revolving around us. So how to cope up with these technologies, that we will illustrate in today's discussion. I would like to introduce first of all why there has been a paradigm shift from the last, we can say, last decade, in terms of data analytics or machine learning, or in terms of artificial neural networks, and many things are revolving around us. So in this context, you see that from the last one decade, there has been exponential increase in usage of smart devices, and all of these smart devices are generating a huge amount of data. And to provide some sort of inferences, or to provide or to make certain predictions, or to make efficient decisions, what we require is that we require that those systems should be automated. And nowadays we are moving from industry 4.0 to industry 5.0 in the years to come, and this will make a huge we can say burden on the researchers to deploy different types of applications in terms of smart applications, smart robotics, and many things are coming on this particular part. So convolution neural networks can play an important role for all those applications, because it's based upon artificial neural networks, and it deals mainly with the images that are around us. And you see that images that are around us, that contains a useful information, and it consisting of many types of attributes that we can process, that we can make it out a certain we can say certain rules and regulations are there. We can make efficient decisions from all those images itself. So it's all about playing with the images as far as convolution neural networks is concerned. And especially we are talking about convolution neural networks for IoT applications, that is industrial Internet of Things, or Internet of Things, all these smart applications consisting of various types of gadgets, smart gadgets, which can be used or deployed in different applications. So the agenda of today's discussion is the brief introduction about this CNN, and then we slowly move on to the constituents of CNN, that what are the basic components of CNN and how this CNN will work it out. And then we will put it out all together, how this CNN can be used in our day-to-day life applications. And nowadays we are dealing with many types of applications where we have used this CNN model. So we will start with the very basic. Hello. We will start with the very basic parts. So you see, nowadays we are all around us. There are number of images are there. So you can have pictures like this that we may have to have different types of application all across us. And in this regard, what we require is that in certain contexts, we require classification or retrieval of information from these images, or we will be able to identify different objects in a particular image itself. Like for example, in this image. So I mean to say here that images are all around us, and these images consisting of huge amount of information. So how to cope up or how to take out some sort of.
Just 1 minute. Dear participants, just switch up your video and audio.
So in this context, you can see that from these images, we can extract useful information, and we can make efficient decisions with respect to identification or with respect to making out efficient decisions. So that's the task of CNN. CNN is basically a classifier which is being used for making out efficient information or to take out efficient information from these input images. So the tasks that are associated with CNN is basically about, let's say, about detection of a particular object. Or for example, in this particular image, you can see that there are different there are different objects that are located at here. Like one object is at here, second object is at here, third object, then we have this object, then we have this object. So there are a number of we can say objects that are located in this particular image itself. So how we can use the CNN model for detection of different objects in this particular picture itself. And moreover, it may also be used for classification of these objects. Like for example, in this case, how to classify between these objects that may be located across this particular part. Not only this, we can also make some sort of segmentation with respect to these objects. Like for example, if there is these objects are there, so we can mark the boundaries of these objects in this particular picture itself. Like for example, here also we can mark out the boundaries of this particular object. So these are the some sort of what we call as the functionality, or what we call as we are expecting some sort of functionality or some sort of work to be done by a CNN model itself. So basically, whenever we talk about computer vision problems, so this computer vision problems may consisting of classifications. Like for example, in this particular image, we need to classify So I mean to say here that we needs to specify, like in this case, we need to make some sort of classification with respect to objects. And then in the second part, we needs to make some sort of localization of this particular object. You see in this particular picture, this object is a cat itself, and we need to localize this particular object into this picture itself. So this is also a task that is associated with computer vision problem. Similarly, here also you can see in this particular picture, we have various objects associated. Like this is one of the object, this is one of these objects, this is another object, then this object is also associated. So object detection, classification, localizations, then we have some sort of segmentations is also associated in this computer vision problem. So our task or CNN task in this case is to classify these objects which are located in this particular image itself, and then then maybe some sort of localizations, etc., etc. So I hope now it is clear that why there is a requirement of CNN model, because in these pictures, this picture contains huge amount of information, and this huge amount of information needs to be retrieved by applying some sort of mathematical functions, or by applying some sort of information to retrieve useful inferences from this particular image. So these are the tasks that are associated with CNN model itself. So how does this CNN model will work it out? So let's say we are dealing with some sort of what we call as a training set. Like for example, this training set consisting of input image set. So for any model to work it out, we require some data set, and these data sets may consisting of some sort of training images or training data sets. So these training images or training data set becomes an input to some learning algorithms, and this learning algorithm is based upon some hypothesis. So this hypothesis takes input values as x, and then from this input value, this hypothesis make some we will make some predicted value, and in this predicted value we have, let's say, some value y is there corresponding to the input data set that we have given. Now we try to make the difference between this value y and this value x, that is y minus x. So this y minus x is the predicted observed and expected value, and our task in any learning algorithm is to minimize the difference between y and x, because you see that y minus x is nothing but it is error. So by making or adjustment, or by choosing the correct parameters, that is called as hyperparameters, we try to make the difference between this value of y and x, so that the error can be minimized. And once this error can be minimized, then obviously our learning algorithm would be will be an efficient learning algorithm, which will be used in any scenario. So if there is a difference, high difference, we can say, between this predicted value and this observed value, then we can make certain adjustment with respect to the reorganization of this learning algorithm. So that's why we will adjust some learning factors, or we will make some adjustment with hyperparameters and tune those parameters so that the difference between this value y and x can be minimized. So this is the goal of any learning algorithms as far as the machine learning or deep learning based model is concerned. So basically our task is to classify the input images into different classes. So those classes may be a binary classification, or that may be a multi-class classification. So as far as binary classification is concerned, so we have two labels, yes or no, and in that case there may be certain instances also that we may have to deal with multi-class classification also, and we can use or adopt a different learning algorithm based upon our input parameters. So as far as CNN is concerned, so it consisting of different layers architectures, and different layer architecture consisting of reading out some input features. So on the lower side, we have all the input feature set. Like for example, at here, we have, let's say, this is one input features, this is second input features, this is third input features, and we have nth input features. So from these input features, we will assign some random weights at the initial stage. Let's say it consisting of W1, it's consisting of W2, it's consisting of Wn. And after that, we reach to these intermediate layers. So these intermediate layers performs the task, or they have some sort of functions that will learn from these input features, and then make adjustment with respect to the calculations of some mathematical formulations, and finally we will get out some output. Now this output is compared with the observed, we can say this is called as the predicted value, and this predicted value is again compared with the observed value, and we try to make out the difference between the observed and expected value. Let's say this is a value delta, that is called as error. So our task in this particular scenario is to make the difference between the observed and expected values as minimization. And during this process, again, we will make certain adjustment with respect to the changing of the parameters or hyperparameter at each of these intermediate layers. And again, we train these networks, and this process continues again and again until and unless we did not get a desired level of accuracy. So this is the whole mechanism as far as a generalized neural networks is concerned. So you see that we have some input image. So this input image consisting of representation of this input image in pixel values. So because you see that computer cannot understand this input image. So as far as feed to the neural networks or convolutional neural networks is concerned, so that is we will take pixel values as input values. So these pixel values are arranged in the form of vectors, or we can say have in the form of representation in terms of matrix. So once this values is input as a pixel values in terms of matrix form or algebraic structure, then these are fed to the initial layers. So this initial layer then is a representation of these input images in the form of pixel values. Once these pixel values had been arranged at this initial layer, then this is passed to these intermediate layers, and then we will perform certain task or certain, we can say, mathematical calculation at each of these intermediate layers, and finally we will reach to this final layer, and we will get out some sort of classification that this input image belongs to a particular dog itself. So here it may also be possible that let's say if this input image is fed into this CNN model, and then this CNN model tells this as a cat. So it means to say in that case we have to adjust some sort of hyperparameters or tune of those parameters in such a way so that we can easily make out classification of this input image as a dog as a final representation. So I mean to say here that from this input image, we will be able to send it out. It means to say that so it means to say that we will have this input image, and from this input image is represented in the form of intermediate matrix form, and from this intermediate matrix form we will be able to we can say we will be able to process and manipulate the information, and then it is passed to this each of these intermediate layers, and we will again make out some sort of adjustment with different parameters, and finally we will get out some final output from this particular we can say networks itself. So if we talk about training of any convolution neural networks, so this is a very simple process. So it consisting of two paths basically. One is this forward path, second is called as this backward path. So in forward path you can see that we will start from this lower layer. So these are input feature sets. So let's say x1, x2, x3 up to xt's are input feature sets. So from these input feature set we will have some features which are more relevant for making out classification. So the features which are more relevant may be assigned some different weight, but initially we assume that all of these input we can say features have same weight or same importance. So we will assign some random weight to all of these x1, x2 up to xt, and then let's say we will have this w1 weight associated with this feature, w2 weight associated with this feature, wd weight associated with these features. Then we will multiply this weight with this feature set w1 x1, then w2 x2, w3 x3, wd xt, and this will becomes an affine transformation. So from this affine transformation, we will have the intermediate results. That is, this sigma is nothing but that is to aggregate all those values at each of these intermediate layers. So this is called as a hidden layer. So this hidden layer is a representation of collection of all those we can say input feature sets, and from this input feature set, if we will be able to make out adjustment with respect to the weight for these input feature set, then these are aggregated and pass on to this intermediate hidden layer itself, and finally we will have some output associated from this training data set. So we will get some, we can say, output that is called as a y, and we have some output that is input that is called as a x. So we will take the difference between this y and x. Let's say this delta is there, delta is y minus x. So this is called as error. So this error function is nothing but it is defined as the difference between the observed and expected value, predicted and expected value. So again, if we have to reduce this error, because our task is that the x should be almost be equal to y, then only then we can say that our trained model is working very efficiently or accurately. So we will have backward pass. We will tune those parameters again, and then apply the training process, and then we will tune those parameters, and then again apply this forward pass, again calculate the value of y, take out the difference between y and x, and then again backward pass. So you can see that this process will repeat over and again many times until we reach a desired level of accuracy. So that's why you can see that in the backward pass we computes the gradient and updates the parameters. So here the concept of gradient descent comes into play. So gradient descent is nothing but we have to differentiate the error with respect to the change in the value of the learning rate. So this is curly e by curly eta, and then we will change the learning rate. It means we will update the parameters, and starting from the parameters at the top layer, then we will move on the backward part, and then this process will be repeated over and again for finite number of times until and unless we reach to the desired level of accuracy. So this is the whole mechanism of training out a CNN model in any generalized scenario for a particular case itself. So the input for any CNN model is basically, as I have already told, that is, it is a matrix form. This matrix form is consisting of pixel value associated with that. For example, let's say an image of a certain height and width that can be represented in the form of grid-like structure. So these grid-like structure is representation of cells, and these cells have some pixel value. So you can see that this is the first cell, this is second cell, third cell, fourth cell, and fifth cell. So each of these cell represents the pixel values, and if we change the order of rows and columns, then the input will be completely be different. So this will becomes as an input value, and this input value will be fed to a CNN model. So this grid-like structure is nothing but this is an array of pixel values. So these pixel values are represented as a one-dimensional vector. This is another one-dimensional vector, and then we have another one-dimensional vector. So these different dimension vectors are fed as an input to this CNN model, and these vectors are nothing but they are representing the pixel values of each input image. So the data in each grid must have a sequence among them, that is sequential data. So there must be some sequence associated with that. So for example, in this case, this left hand side one dimensional vector is representing this black portion of the image, and then these 0 0 zeros are representing the second, third, or fourth one dimensional vectors that is used to represent this white portion in this particular image itself. And similarly, on the right hand side again, we will have some pixel value which is representing the black portion of this input image. So this is the representation of this what we call as data associated for CNN model. So now generalized question arises in our mind is that how a CNN model or why there is a requirement of CNN model for processing out the input information. So you can see that if we have to talk with if we have to talk with only small number of images, then we have only few number of features. So for example, in this case, you can see that a certain images has height, width, and this number of channels that are representing whether we are dealing with RGB image or whether we are dealing with blue scale images. So these number of features are associated as an input to this particular, we can say, for a particular CNN model itself. So, but on the other side, you can see that this particular image consisting of a huge amount of information or large amount of information, and it consisting of these number of we can say attributes, that is height, width, and then we have the number of channels. So these number of features are associated with this particular image. So because this image consisting of large amount of information associated, so we have these number of we can say billion number of parameters, and these number of neurons, or we can say hidden layers neurons are there, which can be represented for finding out there is a requirement of this type of environment for processing out this information. So if we have to deal with RGB image, then we have to deal with these three type, we can say three attributes is used to represent that we are dealing with RGB attributes. So we are not dealing with a grayscale image, but rather we are dealing with this RGB image. But on the other side, if we have to deal with only one channel, then we have to deal with this type of image, that is grayscale image. But here we have three channels are associated for representation of an image in this particular context. Now you can see that if we have to deal with uh, uh, different layers of CNN model, so that consisting of different layers, and each of these layers has different functionalities. So you can see that if we have to deal with an input images like this, let's say this is input image. So this input image has certain dimensions. So dimensions are, let's say, 28 by 28 by 1. So this consisting of a grayscale image that is only consisting of one channel. So this input image will be processed by different layers of CNN, and one of those layer is pre-processing layer. Second layer is consisting of convolution layers. Third is about pooling layer. Then we have how to deal with non-linearity part of clustering and classification of this data. Then we have fully connected layers, and finally we will have the softmax layer. So all in all, you can see that from this input image, we have to process various constituents with respect to the constituent from different layers, and then from these layers the information is processed in a sequential manner from these input images. So we will go one by one what is the task of these different layers in this input from this input image. So you can see that image set is divided into two parts, that is training and testing sets, and then images are flattened and these pixels are put into an array. So these are basically we have to deal with array, and those arrays consisting of representation of an image in one dimensional form or one dimensional vectors, and then our task is to reduce the noise in the image. So noise is basically unwanted information from the input image, and we have different techniques to reduce the noise in the image. And the second layer is convolution layer. So this convolution layer is nothing but it is just about scanning an image from left to right using some magnifying glass. So convolution operators would be performed on these input images, that is to apply this dot product between input and kernel, and it is denoted by some operation which is called as a star operation. So how this star operation would be performed is that we have some filter information you see that each filter in convolution layer is a grid of discrete numbers, and filter are usually of the size 3 by 3, 5 by 5, or 7 by 7. So whenever a filter is placed on the image, then the convolution is basically the middle pixel being estimated using the surrounding pixel value. So our task in this case is that if we place a filter on the image, then the convolution is basically the middle pixel values, which is to be estimated using surrounding pixels. So for example, in this case, you can see that this is the input image, and we have 2D convolution operations on 4x4 input image using 2x2 filters. So if we apply this 2x2 filter on this input image, so what our task is to find out a dot product of this 2x2 filter with respect to this image itself, right? So size of this filter is 2x2. So apply this filter on this on this 4x4 image itself. So we scan this image from left to right and find out the values, find out the dot product. So if we apply this filter on this input image, so the first result that comes is here in this case is 4 after applying of this convolution operation. Then after this we apply again this input, we can say filter on this input image, and again we will get out the dot product and we get some value here itself. Then we again apply this input filters again at here, and then again we will get out some values at here itself. So it means to say, if we apply this input filters on this input images from left to right, then we will be able to get out some values in this intermediate results. So we go on applying this filter on this input images. We start with this in the next round, and then we will get some value at here, like here. Similarly, we apply this filter again on this using the dot product. Again, we get some value. Then we apply this filter at here on the extreme right hand side, and then we will get it out at here. So you can see that we start from the extreme left hand side corner of this input image, and then apply this filter, and then we get some value. Then we go on to the next part, apply this filter, we get the next value. Then we apply this filter at here, then we get this value. Similarly at here, once this initial row has been finished, then we start from the left hand side again, we get some value, then we again apply at here, then we'll get this value, then we apply at here, then we get this value. Similarly apply on the extreme left hand side corner this input filters, then we will get this value, then we will apply at here, then we will get this value, then we will get or we will apply it at on the extreme right hand side, then we will get this value. So you can see that by continuous operation of this 2x2 filter on this 2D convolution operation from left to right, so we will be able to process the information from left to right, and then this intermediate results is placed on this we can say on this matrix form, and then we will be able to have the first pass associated with that. So general question in our mind comes is that how we can use or how we can choose the size of this filter which is to be fitted or which is to be operated on this input image. So we can apply different filters, and using those different filters we will be able to extract a useful information from this input image, and then we can perform different tasks. For example, if we have to have edge detection mechanism, if we have to have object detection, or we have to have some blurring or enhance the pixel values of a particular image itself. So there are number of filters that are associated that we can use on these input images, and we can get out different results in a convolution operation. So let's say if we have a vertical edge detection part, so using a vertical edge detection can be used, can be, we can say, can be used in this particular context. Like for example, in this case, we will have this input image, and from this input image, The extreme left hand side shows the white portion, because this is a representation of the pixel values of the image, and the extreme right hand side we have this this portion. And then we will choose a filter at here. We take a dot product of this input image with this input filters, and then once we apply these operations, so we will get out this value. So in this case, you can see that we will get the extreme left hand side as a black portion, and in between this we have this white portion. So 10 in this case is a white color pixel value, and 0 is the gray pixel value, and -1 is the black portion, like here in this particular case. And finally we will get out this particular portion where we have a white portion as a 10 and 0 as a grayscale. So these zeros are representation of this grayscale part, and this white portion is representation of the white color pixel value associated that on this particular image itself. So we can apply different filters on the input image. So for example, here we have this input image, here we have this filter. So we take dot product from the input pixel values of this image, apply the pixel value, apply this filter, and then we will get out blur that particular image. So this is a, we can say, filter that has been chosen, which is applied on this input image set. And from this input image set, once we applied this filter, so this image becomes blurred. So similarly, if we have to have the edge detection from this input image, so we apply this type of filters. So using this filter, we take the dot product of this input image, and we will able to detect the edges associated in this particular image itself. So it all depends on what is the size of this we can say filter, and how we apply this filter, so that we will get out the information from this input image, and then we will be able to detect the edges from this input image set. So the next part is how we can choose different parameters for finding out a for finding out a or the accuracy in our trained model. So these parameters which we can tune in convolution layers are called as the hyperparameters, which determines the network structures and the variables which determines how the network can be trained. So we can in any convolution layers we can choose that what are the number of filters associated with that, what is the filter size, how the padding, and what is the stride. So we will go one by one all of this. So padding is nothing but it is amount of zero value pixel value that is to be added into image, because you see when a small image goes through a deep convolution neural networks, then it may happen that in certain cases it would diminish early on, and a few convolution layers there may be a problem association with that. So padding is added to make the output size to be same as the input image size set, and mostly all of these zero value pixel values are added as padding. So it is also called as zero padding value. So padding is basically used to make the size of the input image so that it should not be diminished during the convolution operation, because it has to go a large number of operations. So there may be a case that this image may becomes diminished, and we will be not be able to get anything from the input image. So to make out the convenience from this particular part, padding has been added. The second part is stride. So stride is the amount of pixels by which the filter moves over image. So different stride values can be provided for a horizontal and vertical directions. And we can say the more the strides, smaller the output image size is there. And in the convolution layer, the example of stride 1 has been taken in our example itself. So you can see, let's say we have this input image, let's say 6 by 6 by 3 image set is there. Let's say this image set is there, and we apply a 3 by 3 by 3 filters on this particular image. So this filter is applied on this input image, and we will get out this as an output part. So we can say that if we can apply multiple number of filters, so let's say this as input image, and we apply this convolution operation. So from this this is the input size of the input image, like we have 32 by 32 by 3. So this consisting of RGB image itself. And after convolution operations, we will be able to find out an activation map. So this activation map is nothing but we can change the size of the filter, we get out different convolution. Again, we change the size of the filter, again we get the second convolution. So all these convolutions can be placed just like horizontal or vertical, we can say stride, or vertical, we can say vertical slides. So these are used to represent that how with the application, with the change in the size of the input image, with the change in the size of the input kernel or input filters, we can make out efficient provision of selection, and then making out efficient, we can say classification with respect to the input size image, and then we can place all those activation into different parts, just like an horizontal stride of different tiles. So the next part is a pooling layer. So pooling layer is nothing but when we apply the convolution operations, so we will get out a huge amount of information. So the pooling part is to reduce the amount of information in each feature obtained in the convolution layer, while we need to maintain the most useful information. So pooling layers will reduce the number of parameters when the images are too large. So there are two types of basically types of pooling mechanism that are used in this convolution operation. So one is called as max pooling, second is called as average pooling. So in case of max pooling, we calculate the maximum value for each patch of the feature map, and then in the case of average pooling, we will calculate the average value of each patch on the feature map. So using the part of this convolution operations, we can find out what will be the maximum value for each patch, and on the other hand we can also find out what is the average value for each patch, because out of all those features or out of all those operations which has been performed, it may be possible that only the relevant information is required to make out efficient decisions. So that's why we choose only the maximum value or maximum dominant component which can be used for finding out what is the maximum value from the input operations. Similarly, in some cases, it may be possible that some of the components are most dominating and some of the components are only minimum contribution in terms of finding out the overall solutions. So that's why we will take only the average values of all these components and then perform the final task. So for example, if we are going to apply the max pooling operations, so using the max pooling operation, you can see that from this input image, we have to find out the maximum value association. So using this maximum value, you can see that from this value, we have to find out the maximum value, and this we will apply this maximum function. So this maximum function is used to take the maximum value from this input image set. So for example, in this case, if we will have this 1 3 minus 2 0, so we will apply this max part. So using this max part, you can see this maximum value 3 is chosen. Similarly, on this part again, we will choose the maximum value from this. You can see the maximum value that has been there is 3. Similarly, on this side, we will choose again the maximum value. So this value is 3. So you can see that although we have this huge, although we have this 2 by 2 matrix, that is 4 entries are there, but out of these 4 entries, we choose only the maximum value, and from this maximum value that has been chosen is 3. So you can see that out of these 4 values, we can have only one value, that is 3, that is the most dominating part. So we take this 3 as an input values, and rest of the value had been discarded. So in this way, using this maximum max pooling, we keep only the most dominating part, and rest of the information has been discarded. And using the concept of this max pooling, we will be able to make out we can say useful information or useful inferences. Then in second part is that we have to take care of non-linearity part also. So non-linearity part is all about defining out non-linear functions. So it allows the neural networks to learn non-linear mapping also. So non-linear mapping is used about that how we can choose the different activation functions that take real valued functions or real valued as an input and squash it into the smaller range, such as between 0 and 1 or 1:1. So you can see in the absence of non-linearity, a stacked network of weight layer is equivalent to linear mapping from the input domain to the output domain, so which will be of no use. So these activation functions that had been used in deep neural networks are differentiables to enable class child. So these are used to take error function back propagations. So there are different types of non-linear activation functions. So these non-linear activation functions are can be defined as a sigmoid or maybe 10H, or there may be algebraic sigmoid, or there may be a ReLU functions. So these functions can be defined in such a manner so that we will be able to differentiate between input values as per the requirement. So for example, you can see that all those in this ReLU function, that is rectified linear unit. So all those negative values are put at 0, and then all those positive values are kept as positive. So similarly, sigmoid function is also can be defined as a form of non-linearity part. Our 10H function has also been defined as a non-linearity part. Similarly, algebraic sigmoid can also be defined as a non-linearity part. So different functions have different functionality, and for example, these sigmoid functions take in a real number add as input value and output the values between 0 and 1. So it can be defined as a with the help of mathematical calculation, that is 1 upon 1 plus e minus x. So all in all, its value, whole of this we can say value that are associated with this can be segregated between closed interval, that is 0 and 1. Similarly, this 10H function can be defined, that is hyperbolic tangent function, that is squares the value input values between -1 and 1. So its mathematical formulation can be defined between by this particular formula, that is e ki power x minus e ki power minus x upon e ki power x plus e ki power minus x. So you can easily find it out that if we have to squash the value pixel values in between this range, that is 0 1 or -1:1. So if we have to take the value from 0 1, like for example in this case, then it is we can use this sigmoid function. Or if we have to squash the value between -1 and +1, then we have to squash it just like this. So this is 10H part. Similarly, we can also use this algebraic sigmoid. So this algebraic sigmoid is again map the input value with range between -1 and 1, and its mathematical formulation is x upon under root 1 plus x square. So most important part that has been used is for finding out nonlinearity in case of this CNN model is rectified linear unit. So this is ReLU. So this is a simple activation function, and its special practical importance of is because of its quick computation. So this function take the value all those negative values to 0, and all those positive value as positive. So for example, here you can see that all those negative values has been mapped on this 0 itself, and all those positive values are obviously taken as on this positive side itself. So because of its quick computation time, this non-linearity part that is used to take care of in any activation function, most of the times we have to deal with this ReLU part, that is rectified linear unit. So this is the its maximum its formulation can be defined as maximum value be between 0 and 1, between 0 and x, right? So you can see that if we have to deal with this type of part, so we have to take care of the maximum value between this part, And finally, we have the fully connected output layers with softmax functions. So fully connected layers connect every neuron in one layer to every neuron in another layers. So it is a principle in this traditional multi-layer perceptron neural networks. So the flattened matrix goes through a fully connected layer to classify the image, and softmax function again is an activation function that turns the member in fully connected layers into probability that sums up to 1. So it means to say that the softmax function is a special type of function which will add the probability of fully connected layers to some values between 0 and 1, so that if we add up all these probability, then all these probability will add up to 1. So it is used when there are multiple classes for classification, and softmax function output a vector that represents the probability distributions of a list of potential outcomes. So for example, let's say put it all together. So in nutshell, we can say that whenever we have to deal with convolution neural networks, so this convolution neural networks is nothing but it is consisting of two-dimensional array of pixel values. So these array of pixel values are passed to this CNN model, and we have to identify or classify an input image, whether that input image is X or O. So let's say if this X can be represented just like this, and whether this CNN model is able to detect this X as X or this O as O. So these bright portion that has been represented in this X are nothing but these are matrix representation of the input pixel values of the input image, and from these input image that consisting of pixel value association for this X, we will be able to feed those into this CNN model, and finally we will be able to get out the X value or O value association with that. So our task is that our algorithm should work in such a manner so that this X can be identified as X or this O can be identified as O. So for example, here you can see that this X may have some translation, they may have some act, they may have some scaling, they may have some rotations, they may have some other portions like this O itself. So in all these cases, you can see that there has been some sort of twist or there has been some sort of deviation from the original shape of this X or O. And from this original shape of this X or O, whatever the training model we will adopt in this CNN model. So this CNN model should be able to identify these images as a correct X or correct O. So why there is a requirement of this CNN model? So from here you can see that if we have to identify that these images are similar or not, so it is very, we can say, hard for the computer to say that if two images are similar or not. But CNN model is used in such scenario to make out a distinction whether this image is just like this image or not, because here again we have some pixel value associated with this particular image. Similarly, we have some pixel value associated with this image. So pixel value of this image or this portion will be matched with the pixel value of this portion. And if these pixel values are, we can say, equal, then we will say that this portion is similar to this portion. Otherwise, we will simply say that this portion is not similar to this portion. Similarly, here also, again, these pixel values from this input image will be matched with the pixel value of this input portion. So both these portions are matched, and if these portions are not matched, then we will say that there had been some sort of what we call as uh, deflect, or we can say twist from the original portion of an input image. So if we can see that how a computer can see the images, so you can visualize those images just like this. So for example, in this case, you can see that the computer can visualize these as array of pixel values. So these are nothing but these are ones are the we can say highest pixel values, and these -1s are representation of dark portion. So these this one is matched with this one is matched with this one, and similarly the other portion are matched. So we can see that convolution neural networks match pieces of image. So for example, here you can see that this piece of image is matched with this piece of image, and this piece of image is matched with this piece of image, and this piece of image is matched with this piece of image. So when the images are matched, so we can have distinctions with respect to representation of an image, and that particular portion is used to represent that how these images are used for representation in a particular scenario itself. So it means to say, when we say that this convolution neural networks match this portion of image with this portion of image, so we are simply saying that pixel values of this we can say patch of image is matched with the pixel values of this patch of image, and if both are equal, then we will say that the convolution neural networks works very well, right? So you can see that if we have to match a different portion of an image, then these different portions of image can be matched as per the requirement. So like here, the feature match, features match various portion and image. So for example, at here you can see that each of this portion is a representation, let's say 1, and each of this black portion is a representation of -1. Similarly, here itself also there may be a 1. This is 1. This is -1, 1, 1, and the portion associated with that. Similarly, at here also we have this representation of 1. These are -1, and etc. So what is the mathematics behind filtering or matching behind feature map? So what we will do in this case is line up the feature on the image patch and multiply every image pixel values with the corresponding feature pixels, and add up the values and divide the value by the number of pixels in the image itself. So for example, if we have to match up with this portion, so what we can do is that we will multiply those values and then add up all those values, and then divide by number of features, that is total number of features are 9, and then the whole value has been 1 itself. So this one is matched with this one, so we can say that that had been matched in this particular portion. So whatever the results after convolution by filter has been obtained, so we will put all those values in a matrix form like this, because this is a probability, so this lies between 0 and 1. So if we have to match all those pixel values from here in this manner, so we will match like this. So we will apply this convolution operation at here, and then add up all those values, and then after adding up all those values we will have this probability, and when all of these probability will match up, and finally we will have the feature map association from the input images. So I mean to say here that we can apply these different portions, and then we will cap these values in this matrix forms like this, and then using those portion we will be able to make justifications with respect to finding out how we can make out the distinction between the original image and the final image that we have done in this rectified linear unit for CNN models. So this is again a negative value has been made to 0 value. So all in all, we can say the output of one layer is an input to another layer. Like for example, in this case, the convolution, after this convolution operation, we will pass it to the rectified linear unit, and finally we will apply the max pooling. And using this max pooling, again, we will be able to find out the matrix values associated with that. So this type of scenario is nothing but these layers are repeated many times, and based upon this operation of each and every layer, we will be able to make a distinction. Like for example, in this case, from this input image, we will apply filter, and from this filter, we will pass it to rectify linear unit, and then again we will apply convolution, rectify linear unit, and finally we will apply this pooling operations, and finally we will have this matrix form representation. So we can say that every pixel value in this array has been assigned to whether it belongs to X or O. So these values like this 1.0, 0.55, 0.55, 1.0. So these are arranged as a linear vector. Like for example, here also this is again represented as linear vector. This is also represented as a linear vector. So all those values are to find maximum value which is mapped to this X, or they may be mapped to this O. So these pixels get able to strongly predict that it is X or O, and using those X or O we will be able to detect whether that particular image is belonging to X or O from the input image set. So if the image was an O, then some other pixel value would have gotten highest vote. So based upon this voting mechanism, we will be able to predict whether this input image belongs to X or O, and that is the task of this last layer, that is called as softmax layer. So all in all, we can say this is the functionality of this CNN model, and it is used in wide range of application. Like it can be used for audio classification, it can be used for text classification. It has been widely used for applications in autonomous vehicles. You can see that nowadays people are we can say telling about or shouting about that how this autonomous vehicle or autonomous robot will work it out. So all these autonomous vehicles or autonomous robots will work on the principle of object classification and detection, and these object classification and detection are basically dependent upon how these CNN models has been trained it out for clustering classification or to make out efficient decision making process. So for example, if we talk about autonomous vehicle, then autonomous vehicle will work it out for finding out traffic sign identification, and these traffic sign identification consist of different types of images, and these different types of images consist of a huge amount of data set, and these huge amount of input image data sets can be classified or clustered as per the requirement. So these are some sort of indicative applications, but you can see that far beyond that, CNN model has been used in wide range of application in different network scenarios. So this was the preliminary talk, and I hope that it will be very beneficial for you peoples to apply CNN in your day-to-day life application to solve real-time problems in different contexts. I hope you have enjoyed these lectures. This was the basic preliminary lecture, keeping in view of the audience. And if you have any queries, so I am happy to answer your query. Thank you very much.
Thank you, sir. Nice presentation. So it is so clear explanation is there. So researchers might have enjoyed. I enjoyed a lot. I have a question, sir. Yes.
Yeah, please.
Sir, I want to know what is the purpose of this age detection? Suppose we are detecting the age, which type of benefits will get from that?
Like for example, ma'am, let's say we are moving on a particular road itself, and we have let's say we have to design an autonomous vehicles. I'm giving a very real life example, and this autonomous vehicle has to detect an cyclist on a particular road or pedestrian on the road. So to make an segmentation of that pedestrian, to make the boundary of that pedestrian, or to make the boundary of that cyclist, there must be some mechanism using which edge has to be detected. So once that edge has been detected, so in that scenario, we will be able to find it out that there had been some object in our surrounding, and automatically autonomous vehicle will apply the brake, or maybe make some adjustment with respect to its speed or distance, so that there should not be any collision. So this is a very real life example that in our day life, we have to identify the edge of a particular object so that we can make efficient decision with respect to our surrounding itself.
Okay, sir. I got the point. Initially, I was thinking that means so many research is going on age detection.
Yeah,
So
yeah.
it's the main purpose of that. Again, sir, another doubt I'm having in networks also, we are going for padding. So we are adding some extra bit so that the hackers will be confused. They cannot know the starting point of a packet and ending point of packet. But here, whenever we are using in image and that padding, what is the purpose or main intention?
Main intention is that sometimes what happens na, the size of the image is very less. For example, we are dealing with 4 by 4 image, and this 4 by 4 image has to go different types of conversion operations, then pooling operation, then we have to ReLU operations, filters, and so many operations are there. So there may be possibility that after applications of various types of operations, this image may be diminished, and we will not be able to get any clear, we can say, conclusive evidence that what that particular image is there. So we will add these 00 value, because it's all about with respect to playing out or making out operations on matrix in the form of pixel values. So we will make the size of the image such large so that it cannot be diminished during various operations, intermediate operation on the hidden layers in the convolution operations.
Thank you, sir. So participants from participant side, if anybody wants to ask any questions, you can ask.
Yes, participant can raise hand if they're having any question. Sir, I'm also working in the same area in image processing, and I was using CNN for various applications. One thing I was wondering is that there's a lot of debate about what should be the batch size. And normally it is suggested that we should keep a batch of 32. Like what I've understood is that it is only related to the computation, means computation time. So is there any other, thing also which is affecting the batch size, or is it just the computation time?
No, in my view, it is based upon computational complexity also, because
Yes.
you see that we have to deal with a large amount of huge amount of data that is to be there, and our task in this case is that we should design our error function in such a manner so that if we will be able to differentiate it later on with respect to the change in the learning rate. So if we have to find out curly e by curly eta, it means to say we have to make a lot of adjustment with respect to the tuning of hyperparameters. And our task in this case is to diminish this e part, that is error functions. So for that, we have to design this gradient descent, and we have to make adjustment with respect to finding out the gradient at each and every points, and then make adjustment so that this computational complexity should be reduced. So in my view, computational complexity is the sole criteria for finding out adjustment with respect to the patch size.
Okay, sir. Thanks for your clarification, sir.
Thank you.
Thank you, sir. Sir, switch on your video. We will take one photo and participants also.
Ma'am, one question is there.
Okay.
Let me take that question from participant.
Okay.
Yeah, you can ask your question. Glimpse.
Sir, there is a question that how can the accuracy of our predicted results using these algorithms can be increased?
Yeah, I have already told you about this, that the accuracy of any models is depend upon how we can be able to adjust with respect to the tuning of those hyperparameters. Because you see the input image set, from this input image set we have to make out certain operations, and we have to make different types of we can say training and testing. So one we can say criteria is how we can training and testing part, how much ratio we have to take with training and testing part, and second part is how we can train, how we can tune those hyperparameters like learning rate, or making adjustment with respect to this we can say gradient at various stages. So that is the sole criteria, two criteria that is used to take care of your higher accuracy. Obviously the input data set has to be make out certain ratio with respect to training and testing part.
Thank you, sir.
Okay, thank you.
I request our HOD madam to say a few words to our speaker, Dr. Neeraj sir. Madam, you are here. Okay, maybe.
I think she has lost connection, ma'am.
Okay, okay. Nice.
Yeah, any other questions?
And then, okay, all the participants, you can switch on your video. We can take one photo. I am requesting all the participants to switch on your video. We'll take a photo with Neeraj sir. Thank you, sir, so much for your valuable time, talk, everything, sir. Happy to find you. In future also, sir, we'll invite you for physical any presentation or anything we are conducting. Thank you, sir, for your valuable time very much.
Oh, thank you, ma'am. Have a nice day.
Thank you, sir. Thank you.
Thank you.
Thank you, sir. So now let's welcome our next expert for the day, Mr. Raghunandan Reddy. So I request Padmalya ma'am to formally welcome our expert.
Welcome, sir. You are here. Sir already joined, sir.
Yes, sir has joined.
Hi, yes.
Welcome, sir. So we are very happy to find you here. So time mismatch may be there with you because you are. So very happy to find you, sir. Welcome to our conference ICWSNUCA2021. So just one session got over now. So we are waiting to listen from you. You are data analysis experts. So many researchers are there, sir. Just warm welcome. Just we can start the session.
Hi.
So, yes, sir.
Sorry, go ahead.
Welcome. Just I am requesting Dr. Suravi to introduce you. So after that, you can start the session.
Okay.
So, Mr. Raghunandan Reddy, he works as Senior Research Data Science Analyst at H. Lee Moffitt Cancer Institute and Research Institute, Tampa, Florida, USA. He holds a master's degree in Management Information Systems with a specialization in Business Intelligence and Analytics from University of South Florida, Tampa, Florida, USA. He has about 6 years of experience in data science, healthcare, advanced data analytics, data mining, biostatistics, and health informatics. He works with large-scale databases and informatics platforms to answer various research questions in multiple myeloma research program at Moffitt. His work resulted in 8 conference papers for American Society of Hematology in 2019 and 2020, and 1 peer-reviewed manuscript in eBiomedicine in co-author capacity. Few other works are currently under submission with reputed journals such as Blood Cancer Discovery, Journal of Proteomics Research, etc. He is editor-reviewer for many international journals. Raghunandan's research interests are multiple myeloma, cancer informatics, data mining, and data science. And today, sir, I'll be taking up the topic, data science in cancer for personalized medicines. So, sir, now over to you. Raghunandan, sir, you may start now.
Hi, thank you so much. Thank you so much, Dr. Nayak and Dr. Gupta, for inviting me to this wonderful conference. I'm happy to be presenting here. I know, I mean, it's kind of midnight for me. I hope I don't screw the presentation, but and at the same time, I hope I don't bore you guys. So without much further ado, I can start sharing my screen. So I think it looks like I have problem sharing my screen. It says host disabled participant screen sharing. Any chance you could enable that?
Yes, yes. Ma'am, can you make the co-host? Now you are co-host, you try once more.
Yep, I'm able to share the screen now. Thank you, thank you. So this is going to be a short presentation, and it's going to be a bit quicker, and I'll cover the really important and main points of our data ecosystem, or how we are applying the concept of ubiquitous computing to our research group here at Moffitt Cancer Center. Myself, I'm Raghunandan Reddy Alugubelli. I'm a senior research data analyst here at Moffitt Cancer Center. So I'm part of a huge, diverse, collaborative research group here at Moffitt. And our group name is Multiple Myeloma Working Group. As you can see, our group consists of physicians who are medical oncologists, nurse practitioners, and also wet lab scientists, like, you know, who basically do a lot of experiments, and also data mining and data analytics experts like me. So we are a diverse group who formed and who are working on these data to uncover a lot of unanswered myths in multiple myeloma. So multiple myeloma itself is a blood cancer. It primarily affects white blood cells, and it primarily affects basically plasma cells, and plasma cell is a type of a white blood cell. I work only with this cancer, and 5-year survival rate for multiple myeloma patients is only about 54%, so which is very less. And this is second most common form of blood cancer. So as you know, ubiquitous computing refers to an array of diverse technologies deployed through multiple stages of healthcare delivery, from research, development to patient care. So you might be, if you think about the ubiquitous computing in healthcare setting, you might be seeing a healthcare patient lying in a hospital surrounded by several computers, streaming real-time data to doctors, patients, so that they can take an informed decision on patients' treatment, etc., etc. So in like similar setting, we apply the ubiquitous computing, but in a ex vivo manner, which means outside the body of the patient. Which means, I mean, we don't really treat the patient in our Moffitt multiple myeloma group. but we collect the patient samples, which is basically patient's bone marrow samples. So this is the flow for the multiple myeloma working group database here at Moffitt Cancer Center. So these are the individual patients who come to Moffitt Cancer Center for treatments, and we get the consent from the patient. Consent for what? Consent for bone marrow collection. Like, you know, we obtain the sample of the cancer to do individual assay of different components. So here's a multiple myeloma patient, and we obtain the consent for a bone marrow biopsy. And from here, we separate peripheral blood, which is basically blood in bone marrow, and also bone aspirate, where we have the cancerous cells. And we isolate these cancerous cells, and we do sequencing. Basically, it's called whole exome sequencing, where we study the DNA, which is basically DNA and RNA, to see which part of the DNA is mutated, and also for the RNA to see what exactly, or which genes are causing this cancer pathogenesis. And also at the same time, we treat the individual cancer isolated myeloma cells outside in a lab under microscope with 127 different drugs to see the drug resistance. So, I mean, as you can see, we do a lot of research tests on these bone marrow samples, and we collect a lot of data which gets streamed through multiple different source systems, and everything, all the data flows into a final SQL database on which we do a lot of data analytics, data mining, or I mean, a lot of statistics or machine learning and other stuff. I personally handle this pipeline, which is like, a patient comes here, and I personally handle this clinical data mining pipeline, wherein a patient comes in and we collect all the clinical data through a software called RedCap, where we have more than 10 data abstractors to put in to collect the data, and which gets stored in a software called RedCap. And from there it goes to ETL, and then from there it goes to SQL server, and where we match all the clinical data, tumor phenotypical data, or all the research lab data in a final SQL server on which we do a lot of data analytics, basically. So this is the basically the giant workflow, and this project was on from this goes back to 2010, and we collect. We are actually collecting patients bone marrows, like 150 patients per year from 2010. So if you basically accrue them, it's more like 1,000 patients data, give or take, and it's by far the largest database in terms of clinical data, genotypic data, and mutations data in the world in multiple myeloma. So as I said, a lot of persons like physicians, data mining experts, and scientists, and a lot of collaborative effort went into this to make this excellent data analytics platform, or to build this excellent data ecosystem to answer various research questions and to discover many myths of cancer called multiple myeloma. So this is the multiple myeloma working group clinical database flow. Basically, I handle this clinical data mining flow, basically, where we get the data from this RedCap software, and we ingest this data utilizing a software called SAS. where we do variable mapping and extracting the data into SAS and transforming the data into various subsets, and also loading as production data sets. To save space on database, I mean, we usually code them, code the majority of the variable, like, for example, if the gender is male, we say 0 for male and 1 for female. So we need to transform all those coded variables into the data form when we are doing this. So and also we need to do the variable mapping, because the data collection is done for so many years, and we need to make it consistent. We need to make efforts to see that it's consistent and uniform across multiple stages of data development. And also, we do many iterations of quality analysis of this data, especially like, to see if the dates are correct, and like, and especially like, there are some basic quality analysis errors. For example, you can say the date of death should not be before date of diagnosis. So, I mean, it could be a quality analysis metric. So, I mean, we have like 10 to 15 different quality analysis metrics to see we are getting the data captured correctly. That is basically the same thing, debugging to ensure the sanity. And we store these data tables as production tables. We say production tables because only very few persons, only the data mining experts have access to these production tables, who can basically read and write, who can basically write these production tables. All other users will only be able to query these production tables, just to like, they can get the data, but they cannot write anything or overwrite anything on this. And finally, all these tables are loaded into a SQL server. So this is the clinical data flow. And since I started this job back in 2018, there were several forms to capture the data. So I mean, especially in Moffitt, we have several electronic medical record systems, electronic health medical record systems to capture the data, automated data. But those Cerner systems or those electronic medical record systems does not capture all the discrete data elements. So they only capture basic elements like race, age, sex, ethnicity, and first course of treatment, and labs and some other variables. So it doesn't basically capture all the data that is belonging to the patient. So for the same reason, for allowing us to capture all the clinical data elements, we use this REDCap software, and our data abstractors build these forms and capture all the data elements, for each of our patients. So for especially feasibility of the project, I mean, when they have started, in the version 1, data contained about 3,126 variables. So it's a huge data set. I mean, so 3,126 variables, meaning the raw data set has 3,126 variables, which is like a lot of variables. And version 2 had 2,435 variables. So version 1, 2, I mean, these versioning number, meaning with the time, basically we upped the number of versions to make it more queryable friendly, and also to make the structure user friendly. So basically we started as a giant horizontal table. From there, as the time progressed, we went from the giant horizontal table to the vertical table, so that querying is easy. So if you see in the version 4, we have only 571 variables. So we went from 3,126 variables to 571 variables, which is current version, which is really optimal version. So, I mean, we didn't do any rocket science or magic here. I mean, we just condensed the number of variables by using vertical to horizontal logic. For example, in version 1, the treatment data is captured as treatment 1 to 3, treatment 1 to 20 in 20 different variables. In version 4, we put everything as treatment and we captured it in 20 different rows. So that's something we learned ourselves from version 1 to version 4. And by the way, I mean, when I said 3,126 variables, that means these are all the raw data giant files. And from here, you know, for these raw data files, we add the default data elements, which we get from the original source systems like Cerner or electronic medical record systems. And we try to partition them and break them into different data sets so that the querying is easy. Basically, this is one of the snipping of all the production data sets after we break the data, basically. So, I mean, it's been a bit of time since I updated this slide, but we have much larger file size. And when we are talking about this data system here, this is only clinical data. So there is other aspects of genetic data, mutations data, and a whole lot of other data, which I have not included here because it is handled by my colleagues who are basically bioinformatics engineers. So, I mean, as I said, I handle most of this clinical data pipeline here. So anthropometrics, meaning basically like, you know, data elements like height, weight, BMI, and for that patient. Biopsy is basically, you know, it records biopsies, basically like, you know, all the biopsies which were performed at that patient associated with the biopsy date, and all the findings in that biopsy, especially like, you know, the labs and other stuff. BMT is basically bone marrow transplant. So to further improve the life of this multiple myeloma patient, physicians often go for a bone marrow transplant. So this data set captures if the patient has received a bone marrow transplant. And the next one is comorbidities. If the patient has any diabetes mellitus, like, you know, any like, you know, any serious conditions like, you know, heart problems, kidney problems, or anything like that, that gets recorded here. And cytogenetics is basically, again, it captures the mutations data, especially in chromosomes. You know, I mean, male human beings have X and Y chromosome, and female human beings have XX chromosome. So multiple myeloma, one of the serious risk factors is basically because those chromosomes get altered. So this test aims to capture the chromosomal abnormalities or chromosomal aberrations in this data set. And family, we also tend to capture family variables, basically like, you know, for a patient, we always analyze a patient's family's, you know, cancer history. For example, if a mother or a father has a cancer history, there is always a higher risk chance for the progeny. So the I mean, again, it's a risk. So we always try to capture the family variables here. And HX, DX, meaning the disease history variables, like, you know, the date of diagnosis for that patient. And this is imaging data. Imaging is basically, again, multiple myeloma patients have bone lesions. So all the X-ray data. And the next one is labs data. Labs is basically if a myeloma patient comes into hospital, like, we do all sorts of blood work, like, their blood work, meaning their albumin, their beta-2 globulin, all sorts of, we measure all sorts of different components of these tests. So all those would get stored here. Metastatic disease, like, how much the cancer has spread in that particular patient's body, and those are the variables we capture here. And performance, meaning, like, what is the activity level of that particular multiple myeloma patient, like, is he fully active, or his activities hindered by the cancer. All these variables are in this data set. And the other one is radiation. Some of the bone lesions are like, some of the bone perforations or the holes in the bone are treated by the radiation, and all the data is captured there. And the staging, I mean, you might have seen it in the movies, I mean, where they say this is stage 1 cancer, stage 2 cancer, stage 3, which is more severe type of cancer, all that data here. And treatment data, which is a lot. I mean, right now, multiple myeloma patients are living like, 5 years, 10 years. And in this duration, they tend to undergo through a lot of treatments, a lot of drugs, and that for many years. And all that treatment data is saved here, or recorded here. And vitals, like, date of death, like lost contact date with the hospital, and all those different data components are saved here. So this is the gist, or the idea of what sort of data elements we are creating in this data ecosystem. I mean, you might wonder why we get all these data elements. I mean, these data elements or these data variables serve a lot of purposes, or like, a lot of purpose for any other research investigators to answer various questions. And on the top of the data sets, we build various reports, especially for dashboarding, for easier visualization, especially the reports to showcase what is the disease status of that particular samples which we collected. Like, when we were collecting those samples, what was the disease status for that patients? Like, was it a newly diagnosed, which means like, brand new cancer, or was it a late relapse cancer, like, really has gotten bad? That type of stratification or classification is being done. And also several reports we use for survival data. Survival data is, again, basically like, just the calculating the number of days difference between the date of diagnosis to date of death or date of lost contact date. Like, if the patient is alive, the number of days difference between date of diagnosis to the last follow-up date, and their treatments. And then demographics data. Demographics as in, like, what is the race of that patient? Is he a white person? Is he African American? Is he Asian? And also ethnicity data, like, ethnicity as in if they are Caucasians, or if they are Hispanic people. Like, Hispanic peoples are people from South American or Latin American descent. And we also track a lot of the shipping manifest. I mean, basically, we collect all these samples, and all these different components, all these different, like, whole exome RNA sequencing, it's not done at Moffitt. We basically send them out to different labs, a lab called Hudson Alpha. So we always have to track, like, where were, like, when were our samples were shipped out, and when are we getting the data back? And this whole exome and RNA sequencing data is like huge, like really big data. So we create various reports to track where our samples are in the life cycle or in the data cycle, and all of these reports are built in SAS, especially because of the versatility of SAS, like where it can work with multiple databases seamlessly and works very well. I mean, right now we are working with a lot of SAS, but I think in future we might move towards more of R and Python. Right now we use both of a little bit of SAS and R, but not Python, because Python being open source language and SAS is proprietary, and this is all patient data. I mean, and patient data has PHI concerns here, which is protected health information. So open source languages are not very much encouraged at our institution, but I think things are going to change in future. But what I'm trying to say is we are working a lot on SAS and SAS these days. And we use those dashboards, we use those data sets to build these beautiful dashboards to create a visualization, especially to showcase it to higher ups or higher management or directors or non-technical users. Like, for example, a physician cannot code or cannot program or cannot query the database. So for them, we can showcase this dashboard and they can just go here and filter all the parameters which were here, and then they can download the data. And we have analytics layer with about 25 plus dashboards. So I mean, the dashboard was built upon the top of this database here. So the dashboard sits somewhere here, right? Exactly. We don't have it in this slide, but it's somewhere here, so that it anyone who does filter on the dashboards gets the data from here, and then showcases the appropriate stuff on these dashboards. I mean, as you can see, we have disease status, gender, ethnicity, race. So this is basically one dashboard, and we have 25 plus dashboards here. The main purpose of the dashboards is non-technical users would be able to download the data from these beautiful dashboards. And it also serves as a very wonderful visualization tool. I mean, there are many people who don't like to read or look at the data, bless you, who don't like to read the data, but they want to have look at these dashboards and have an idea of what data is looking like. So so this is basically a business intelligence or data science aspect of our project, which is really interesting to many of our collaborating partners. We also do QCing pipelines, meaning if there are any aberrations with the data that data abstractors have abstracted, some of the data records are dropped, and we have built this parallel QAing pipeline where we drop those wrong records from the data and we append this QC data, so that we have only correct data in there. So these QC pipelines are built in SAS. So finally, you might be wondering, what all this is built for. What do we do with these data ecosystems with which we built from so many years with a highly collaborative effort? So we can do gene expression tests. Gene expression tests, meaning if you take the RNA sequencing data from the bone marrow of a patient, we have 16,000 genes or 17,000 genes for that myeloma cancer cell, and we can see, like, you know, which gene is expressing, or meaning, sorry, excuse me, meaning which gene is has correlation to the survival for that patient. Like, you know, you can tell, like, you know, this particular gene is expressing so much in this cancer patients, and it's highly correlated to the survival of this cancer patient, meaning the higher expression of this gene has been linked to lower survival of this cancer patient. So we can do various gene expression tests, and we can identify these targets, saying that, hey, this gene is linked to lower or inferior survival in multiple myeloma patients. And basically, again, with our friends in pharmaceuticals, we can identify these as a new drug targets, and we can develop new therapies for cancer patients, so that can prolong the survival of these cancer patients. And also developing different frameworks based on treatment data to personalize therapies. So the future is about personalized therapies, meaning not every patient is going to have the same therapy. Each individual patient is going to get their own individual therapy. I mean, physicians, they could look at how the patient is responding to treatment, and know each patient is same. So the future is basically personalized therapy, and the personalized and so personalized therapy, meaning a therapy which is cut or which is designed for a particular or individual patient. And how we design those treatments, depending on their data from all these tests. Like, you know, if he has this particular mutation, this drug is going to work very well for him. If that patient's gene expression, this particular gene expression is increased so much in that patient, then this drug. So I mean, all these different variables going to play a major role in personalized medicine for these cancer patients. That is a reason building data ecosystems with the help of clinical data, genotyping data, and mutations data is going to be of paramount importance in future of designing cancer treatments for each of these individual patients. So this is essentially, in a nutshell, this is going to be the research output of the data ecosystem we created here at Moffitt Cancer Center, especially for multiple myeloma. And I would like to show you, like, you know, some of the cool things we kind of discovered with our data. Like, you know, if you see PFS by best response. So I'd like to explain what is PFS. PFS is basically progression-free survival data. So progression-free survival meaning a brand new, a new cancer patient comes in, he gets a treatment and he responds well, and then he relapses. So multiple myeloma, we don't have cure for that. We are hoping to find the cure, but we don't have it right now. So the patient always relapses at some or the other points. Relapses meaning his cancer, his or her cancer comes back again after the treatment. So we are trying to measure the PFS here. PFS is progression-free survival, meaning the number of days a patient did not have cancer after the treatment. So at some or the other point in future, the cancer comes back to the patient, meaning the patient gets relapsed. So here we stratified patients by progression-free survival by their best response. So best response meaning International Myeloma Working Group has categorized the patient's treatment data into these various different categories. Like, you know, if he responds very well, then he's put into this category, which is PR or worse. if he responds well, he's put into this VGPR or better. VGPR is basically very good partial response. And if he did not respond well, then he's put into this group, which is PR or worse, partial response or worse. So as you can see, progression-free survival data, which is basically is less for the PR or worse group. So that means the patients who did not do well with their first treatment have cancer coming back early when compared to these patients. So you know, these are some of the cool things which we do with the data. I mean, a lot of these works are really under publication. So just to give you a gist, I thought like, you know, I would show you a couple of scenarios how we can use this data as. By the way, this analysis is called Kaplan-Meier survival risk analysis. And if you see this overall survival by age at diagnosis, so you have this variable called age at diagnosis, age when the patient got diagnosed of the cancer. So we grouped this variable into 3 different categories, 51 to 64, greater than or equal to 65, and less than or equal to 51. So if you see, overall survival is basically like, you know, how long did the patient survive after getting the cancer? So if you see here, clearly the older patients are at risk. Like the older patients survive lesser, and followed by 51 to 64, and followed by younger patients. Younger patients live more when they get diagnosed with cancer. So this is again the cool data which I wanted to show, where we stratified the survival by age of diagnosis. And this is another slide, like, you know, where we stratified overall survival by race. Here, when we do race studies, we always categorize or stratify patients into white and African Americans. I mean, we have tiny bit of Asians here, like very low in numbers, so we don't usually show them here. So here in overall survival stratified by race, the white people have inferior or lower overall survival when compared to African Americans. So African Americans tend to live longer if they were provided as same treatment as Caucasians or white people. So if you can see, the white population has lesser survival when compared to African American population in multiple myeloma as a disease or as a cancer. So I think and this is one of the other dashboards where we track like, you know, the number of bone marrow samples. We track from, like, you know, the number of collections, bone marrow collections we get from the patients year wise, like, you know, in 2011, 2012, 2013, 2019. Again, this is not so updated number. We have quite a bit higher numbers here in 2019, and 2020 has slowed us down a bit because of COVID. So I mean, we do all these dashboarding and as part of data ecosystem. So I think, yeah, this is it. Thank you. So with that being said, anyone has any questions? I know, I mean, this is a lot to take, and this is a lot of biology integrated with a lot of data. So I assume since you are a lot of engineering focused, this might be too much for you, but feel free to ask me any question. I mean, all my colleagues here in data mining and data analytics, we all have a solid engineering background like you guys. But it is just that we are working to cure this cancer or make patients' lives better.
Yeah, any questions from the participants? That's a wonderful session, sir. And we have really realized how beneficial this data analytics is in the analysis regarding this cancer research, and some real practical applications are there. And that is really wonderful. The kind of analysis we have presented, even we can find out the survival rate of the patients. You have compared between white and Asian background and so on. So really a wonderful insight into the topic, and a really practical aspect, how these all what we are studying in theory, data analytics and all, how we are going to implement that for practical purpose. That's really wonderful. And sir, are you also using some new techniques like machine learning or deep learning for this analysis of data?
Yes, yes. So we are currently working on reinforcement learning on our treatment data. That is currently in the books. I mean, that is currently work in progress.
Right, sir. Great. Great, sir.
Thank you, sir. So much nice presentation. We could learn deep analysis about the data. Normally, I am working in a sensor network, so data analysis, deep knowledge I didn't have. But clearly, I saw that in which way you are doing the work. It is fantastic, sir. Very happy that I listening this session. Welcome you, sir. For next also, we will invite you. We are organizing many FDPs, and this conference series also will maintain, but quite interesting, sir. The way that level of cancer you are telling, no, nowadays the people are prone towards cancer due to the food habit or whatever may be, environment, many parameters are there. But it is very nice presentation, sir. I like.
Thank you, thank you. Thank you for the kind words. I appreciate it.
So deep analysis, if you're not doing, then higher quality journals, we cannot produce the result. So
yes, yes.
Know exactly if you want data, we are knowing that how to analyze properly. So now diseases are quite very often, we can get different types of data. Then we can produce the research result.
Yes, yes. Building the data ecosystem is itself like the toughest thing here.
Any other participants, if they're interested in asking any question to the expert, they are most welcome.
Yeah, please go ahead.
Now midnight, despite of that, that you are
yes
taking a nice session. I appreciate you, sir, very much. Nobody just raised a hand, madam.
Yes,
no,
just I'm waiting for 2 minutes. If there is any question, we'll definitely take up.
Yeah, for many of them, it's new domain. The cancer data is complex, so I definitely understand the apprehension of not asking the questions.
Yes, sir. And basically, when we do experiments, we take public data sets. Many are available, so we try to explore them only. But then, even if we do not whether it will be actually useful, because application is limited to a research paper or project. Okay, but your work is really commendable, because you are actually doing something which is directly going to be applied and useful for all. So that's really nice.
This is midnight, no, sir? Can we take one photo with you? I don't know.
Yeah, go ahead. I mean, I'm kind of mildly prepared, but I hope this is okay. Okay, so I'll have to switch on my. Okay.
So I request participants to please switch on their cameras for a while.
Yeah, okay, sir. Yes, they have taken the photos. So thank you, sir, very much. So
Thank you.
see you once again for next or conference, whatever we are organizing. Thank you, sir, so much. Namaskar, sir.
Thank you. Bye-bye.
So now we can leave. Tomorrow that session will start exactly 9:45 our inaugural. So before 15 minutes, all the participants I'm requesting to join so that everything will go smoothly. 3 keynote speakers are there and they are all good speakers. So listen to them and we'll get huge research ideas from Udgata sir, Ping sir, and Amit Mishra. He is also working in a government university. They are having huge project on this wireless sensor networks and IoT. Just I'm requesting everybody not to miss that chance. They are all good speakers. Thank you all. See you tomorrow. Anybody wants to speak or anything to tell?
Yes, if any participant is having any query, he or she may ask.
Ma'am, is it necessary to switch on the camera while presenting paper?
If you will present with camera, that will be nice. So be prepared for that because anyway that we have to send some photos to publisher. So if it is a photo is there, it will be good.
Thank you, ma'am.
Ma'am, how much time is regarded for each presentation? Like, how much time would we get?
10 minutes followed by question and answer.
Okay.
10 minutes presentation, maybe 5 minutes for question and answer.
Okay.
Just be on time and that the speakers are good. So tomorrow we can enjoy the talk. Thank you all.
Ma'am, the presentation will be in which order, ma'am? Based on the ID number or?
No, in which order we have given the session schedule, that order only. Because we have categorized in the according to the area. So in a particular area, we have put some papers. So according to that session schedule, we will maintain.
Will you send the schedule, madam? Will you send or already sent, ma'am?
Already shared in the group, already updated in the website. So you can refer anywhere.
Okay, ma'am. Okay. Thank you.
Madam, excuse me, for all participants, we have different links that also we will post in the evening. So carefully select that.
No, actually this session, this link, it will continue completely inaugural and followed by some sessions that will notify in the WhatsApp group. And one parallel session will be there for a few sessions. So just see the clearly 2 parallel session will be there in which link you have to join. Just go through the, we will update in the WhatsApp group. So up to inaugural and this keynote speaker, one link will be used. But after this launch, 2 parallel session will be there. The same link, apart from this link, another link will be there. We'll give the guidelines in the WhatsApp group.
Okay, ma'am. Thank you, ma'am.
Anything else? Otherwise, I'll end the meeting.